Well, section 7.3 is here, and I apologize in advance, but things are only going to get stranger at this point. Um, just keep with me. Give your best try, like I said before, to be kind of open-minded in this, and ask as many questions as you want when you see me in class. Now, what we're starting to see in this section is that this wave-particle duality that we saw for light isn't just for light. That it's also an aspect of electrons. Now try and wrap your mind around that for a moment. Okay? You can think of, it's weird enough to think of light as having particle-like properties, meaning it's kind of a packet. It's not just pure energy, but it's little packets of energy. And I can almost wrap my mind around that, but now I have to think of an object like an electron. So that's some physical object with mass to it, right? Light doesn't have mass. Electromagnetic radiation, no mass. But light, or electrons, have mass, so they exist. They're physical objects, and yet they have aspects to them that behave like energy does, has wave type nature. So let's take a look at that. To kind of look at how light and electrons interact with each other, we have a whole field of study that's actually referred to as atomic spectroscopy. And this is just the study of how electromagnetic radiation is absorbed and emitted by atoms. When they first looked into this field of study, they didn't realize that electrons were really what was governing this type of activity. Now, what we see with atomic spectroscopy is just light energy being absorbed, light energy being radiated out from atoms, and when atoms absorb energy, actually of any different kind, they can radiate that energy out again as visible light. They can also radiate it out as non-visible light, as UV or microwave or IR, heat energy, that sort of thing. But it's interesting to see that they can kind of convert this as well. So for instance, if I heat things up hot enough, that heat energy is going to get translated into visible light. It's going to glow. It's going to glow red, and the hotter it gets and the more energy it's putting out, it's going to glow even brighter colors all the way until we get white light glowing out of this. You can have things that absorb light. All the UV black light, it's just UV light, ultraviolet, and you can shine ultraviolet light on different chemical dyes, and those chemical dyes will then emit light in the visible spectrum. You don't actually see black light. That's why they call it black light, right? There's kind of a purplish hue to it, but that's just what's leaking in at the edge of the ultraviolet spectrum into the visible. But when objects that absorb black light and then emit light do that, it looks like they glow when you shine a black light on them. They're just absorbing the incident black light, UV radiation, and re-emitting it in color. One of the more fascinating, I never thought about this as an aspect, but I was looking for nice pictures to display on this. I ran into this thing of people now getting tattoos that have ink that is active with black light. So it glows in the dark under black light. So people have just a regular kind of tattoo with whatever markings and colors, but shine black light on it in the dark, and you can see little lines around the stars. The stars are outlined in colors. There's little sparkles are outlined in a substance that comes back as red. So people are doing amazing, bizarre, and strange sort of things with this, such as this guy had a picture of what he had tattooed to his hand, which is basically an image of the bones underneath the skin, which you can't see at all in normal light because this is not absorbing any visible light or reflecting any visible light back any differently in his hand. It's transparent to regular light, but when you turn a UV light on, the dyes absorb that ultraviolet radiation and re-emit it as kind of a bluish purple, And so in the dark with a black light, you actually see a glowing skeletal outline where this person's hand and skin is, just because of that set of tattoo dyes that he's put on it. I don't know, it just seemed kind of fascinating to me. Electrical energy also is something everybody's seen. Anytime you've seen a neon light or halogen, these nice glowing lights that people put up of different colors, that's just electrical discharge, spark type energy being given to elements, atoms of elements that are then radiating that light back out again in a visible spectrum. So, talking about spectrums and the electrical discharge, we can make these things called arc lamps. And effectively what this is just we charge these up to a couple thousand volts, supplying electrical energy to the gases, the electrical energy of specific things like hydrogen and helium and sodium and that sort of thing caught up inside of a tube, takes in that electrical energy and emits visible energy from those atoms. And the interesting aspect of this is that these tubes only have one kind of element. So instead of air, which is nitrogen and carbon dioxide and oxygen, and a couple of noble gases, probably some volatile organics, all the things that you have in air at a given time has a lot of different things in it. But if you have a discharge of this, all you're seeing is the light from one specific element's atoms. So that actually gives you some kind of interesting results. If we split that light up through sending the light through a slit to kind of get it going in one direction, put it through a prism to break it up into its colors, and then display that on a screen that we can see, what we see is for an individual atom like helium compared to a white light emitting source, which is emitting light in all colors, the helium atoms are only emitting light in very small, discrete colors. So I see a little bit of light emitted in reddish, orange, yellow, and then a couple in this kind of light blue and dark blue purplish spectrum. And for barium, a different atom with more electrons, interestingly enough, although we're not quite connecting that yet, but barium has all of these other additional lines, but still very discrete individual sets of lines instead of a continuous spectrum of light. So we're only seeing very specific energy levels of light being radiated out of these atoms. Well, how can we kind of explain this? Well, scientist named Johannes Rydberg came up with a way to predict this. Did a lot of experiments, looked at a lot of spectra, and for the hydrogen atoms, at least, he was able to come up with an equation that gave a relationship between the wavelength, so we're looking at color of light emitted, a constant, and a couple of other constants that were whole number integers. So like 3 and 2 or 4 and 1, that sort of thing. And you could predict that there would be specific bands of color based on specific levels. Basically 2 and 3 and 4 and 1. So these represented different states, evidently, that the hydrogen atom could emit light from. So we had to come up with a model that explained what in the world this line spectrum that we see on the previous slide, where we have very discrete specific energy levels, and the fact that we can predict that by kind of integer multiple changes of energy. How do we explain that in a model that explains what must be going on? Well, one way to look at that is kind of a model, and this isn't the most modern interpretation, but it's a very direct transition from the old classical mechanics to a transition to quantum mechanics, is thinking of electrons as being a certain distance from the nucleus. Right? This is the nucleus here in the center. And the electrons are certain distances away from that nucleus, and when they absorb energy, they move away from the center. So say from this level that we can refer to as level 1, maybe all the way out to level 4, and that's from absorbing light. They move farther away. You can kind of think of this, if you're thinking in terms of physics and energy, of potential energy. Separation of charges is a potential energy that was converted from the light energy that struck this particular atom. But in any case, you don't need to think about it that way. It's just one way to think of it if you're in physics. But so the electron moves out when it absorbs energy, and when it falls back closer, it gives up some of that energy as visible light if it falls from certain areas. It turns out to fall from an area at 3 or state 4 or state 5 back to state 2 gives me visible light. And short falls, short distances between n equals 2 and n equals 3 and n equals 2, and that Rydberg equation that we just saw would give me light that's red. And from 4 to level 2 would give me light that's kind of a blue-green. And from 5 back to 2, if electron moves that particular distance, then we're seeing violet. Now, think about this for a second. I'm only seeing very, very specific colors, meaning that these particular states are where the atoms can move to and fall from. But the fact that I don't see any colors in here, I don't see any light emitted anywhere in between those lines, says that none of those spacing distances between exist. The electron is never in any of those locations. If it was, I would see a color band there. Even if it was only there for a fraction of a second, it could then be, say here, fall back to 2, and then this distance would correspond to some color between this purple and this green, from 5 to 4. But since it's not there, that means the electron is never there. So what this model predicts, and what bears out through experimentation, is that electrons are only going to exist in very specific states, very specific spacings. And even more confusingly, the electron does not exist between these states. It never is in between, say, state 5 and state 4, distance 5 and distance 4 here. Well, it's moving, though, between those points. If it never exists in between, but it's moving from point A to point B, what you effectively have is, I'm going from here to here, but I'm never in between. So I disappear from point A, reappear at point B, having never existed anywhere between those 2 points. And that's how electrons exist on that scale. So on the atomic scale, in a lot of ways, we can think of these electrons almost as units in a pegboard. I can have an electron in one spot or another, but not in between, which is completely contrary to how we kind of see the universe on a macroscopic scale, where everything's continuous and motion is continuous, and I can put my hand in front of myself or on the side and anywhere in between. Electrons just aren't like that. They have very specific spots, and that's it. One practical aspect that we kind of throw in here at this point is, since each atom has its own kind of set of electrons, it has its own set of where those electrons can specifically be or not be. So the color that comes off of atoms when you give them energy, say by heating them in a flame, so that they can give off energy when they release that energy, is very specifically tied into the electrons present in that particular element's atoms. So I can take sodium and lithium and all these other different elements and heat them in a flame and see very specific colors given off by them, depending on what exactly the element is that I'm heating. So I can identify elements specifically by their color. And this atomic spectroscopy aspect is actually used by modern instruments to detect things like mercury and lead and even calcium in hard water and that sort of thing. All right, so we're getting closer to understanding what an electron is. It's only going to get weirder from here still, I apologize, but at least we're getting closer to understanding how this works. What we know so far about electrons, very small. We know they can exist in multiple states at once. That's that Schrodinger's half-dead cat thing. We know that they can only exist in specific states within the atoms and move between those states without ever occupying the space between. We know that from the line spectra that we observe from electric discharge lamps.